I'm going to talk to you about light-emitting diodes, LEDs. Red LEDs emit photons with a wavelength of 625 nanometers. The energy of each photon is hc over lambda, so in other words, Planck's constant times the speed of light divided by the wavelength. Green LEDs give out photons with a wavelength of 525 nanometers. It's a shorter wavelength, so it's a higher energy. Blue LEDs have a wavelength of 470 nanometers, so they, of the three LEDs, they've got most energy. LEDs, now this bit you don't need to know, but it's quite interesting. LEDs are made from semiconductors. Semiconductors used in LEDs are made from silicon, which is just sand, basically. And silicon has been treated so that either has extra electrons, so it's got a negative charge. We say it is an N-type of semiconductor. And we also have P-types of semiconductors where those excess electrons have been removed. And we actually have holes. We have positively charged holes. And the reason that our LED gives out light is because a hole in the P-type of the silicon, the P-type silicon, has combined with an electron which is in the N-type of silicon, and the extra, so they've just annihilated, so combined to create a nothing, and they've given out the extra energy as a photon. Obviously you have to have a junction where the N-type and the P-type of silicon are touching, and you can adjust the energy released at the junction when the electrons and the holes meet, and that's why we can create an LED that gives out red light, or gives out blue light, or gives out green light. Now that can actually happen in reverse as well. So we can create a photovoltaic cell, in other words, a solar cell, using the same materials. What happens there is that we do have a P-type and an N-type of silicon. They both meet at a junction, but this time they absorb a photon. When a photon is absorbed, it creates an electron and a hole. And the way that the semiconductor is designed, the electrons tend to be pushed away from that junction into the N-type silicon, making it more negative, and the holes tend to be pushed into the positive charged P-type silicon and make it more positive. So we create a difference, an imbalance in the charges. So our photovoltaic cell has a difference in charge. We create an electric field across that junction, and that in itself then creates a voltage, a potential difference across the junction. And if we connect something across that junction, then we can actually have a current flowing. So we're going to just quickly look at some experiments. Let's move this so that you can see the readings on these voltmeters. Just turn off the LEDs so that they're not going to disturb us. So what I've got are 2 voltmeters. They are set, you can see, on the 200 millivolt scale. Each one of those is set, so that's the reading. So I'm just going to move this up a little bit so we can see. And for each one of these, I've connected it to an LED. And I'll just put this button cell between the legs of each LED to show you. This is, you should be able to see that's red. I hope you can. And this one is a blue light-emitting diode. Okay. Now, I'm going to demonstrate these light-emitting diodes acting like a photovoltaic cell. I've got a marker here to make sure that I have my LED here, and I'm going to shine some photons at it. I'm going to shine photons from this blue LED. So I've got a blue LED shining photons onto a blue LED. And you can see that reading has moved up to about 46-ish millivolts. I'm not quite sure why it's going down, to be honest. Is that a bit close to see if it stays constant? Around there. Okay, so we've got a reading. For some reason it is roughly constant, but it is going down. I don't know whether there's some fluctuation, whether it will stabilise, or whether maybe the battery's slightly running down. But I've got blue light shining onto a blue LED. I've got a reading about 36 millivolts. What happens if I place my blue LED, shine the blue photons onto my red LED? So remember, there we go, 33 millivolts. So it's less, it's a smaller number. What happens if I try with a red light emitting diode? If I shine my red light emitting diode at my red LED, you can see the reading is actually much, much greater. It's much more efficient. This silicon's much, much more efficient at absorbing those red photons. That junction has been created to be very effective. So I'm getting a reading about 120 millivolts. If I move my red LED across and shine it on my blue light, I'm getting nothing at all. And think about what you know about photons now. Those red photons have got less energy than blue photons. They don't have enough energy to actually create an electron-hole pair inside that blue LED. Those red photons have got less energy. Now I also have a green LED here. So let's see whether that has any effect at all. And as you can see, we're getting a small amount of voltage, 0.6, 0.3, 0.2. So very small, slightly fluctuating reading. So obviously our green photons have got a little bit of energy, and they are able to create some electron hole pairs. How about with my red light? So here we're getting a reading. It's a little bit tricky. I'll point that more effectively. Of about 2.8, 2.9, 3 millivolts with my green light shining on my red LED. So what you hopefully can see, if we move it just slightly closer, we get quite a big jump in the reading. So what you're seeing here is that, first of all, it's really important that we match the energy. Whenever there's an interaction involving photons, we normally have to match the energy of the photon with the energy of whatever interaction is taking place. That's quite an important thing to understand, particularly when we look at energy levels and spectra in future. And also, it's just some evidence that the red photons have got less energy than green photons, and green photons have got less energy than blue photons. And that's it for the moment.